Hi, this is the second lecture in our series on data services in IBM Bluemix. As you recall, in the first lecture we looked at the types of services available and we gave you examples of each type of service. In this lecture, we'll dig a little deeper into some of those services, look at their features to give you in this lecture we'll dig a little deeper into some of these services and their features to give you a better idea of how you can benefit from using these services. So the services we'll be looking at today include the following. The Cloudant NoSQL database service, which as you recall is a document-oriented schemaless data store that's optimized for horizontal scaling. We'll also look at the dashDB service, which is a relational data store that's optimized for complex analytic queries. Then finally, we'll look at the time series database service, which as you recall is a service that's optimized for storing Internet of Things time series data. So let's start off by looking in more detail at the Cloudant NoSQL service. It's a fully managed NoSQL database as a service, which means that you don't have to do any of the database management yourself. The service is available to you on the cloud anytime, anywhere. You just need to provide your code and your data. It's a document-oriented database, as we mentioned earlier, and the document format is JSON. It also comes with a RESTful API, which we will discuss in more detail in a few slides. It can spread data across data centers, devices for scalability and high availability. And we'll talk more about that when we talk about the Cloudant Sync feature. So it's ideal for apps that require massive elastic scalability, high availability, geolocation services, full text search, and occasionally connected users, which means that users need to be able to work offline when they're not connected to the database directly. The Cloudant database service actually grew out of a specific use case, the Large Hadron Collider project. The scientists involved in that project needed a database for distributing large volumes of data to scientists around the world. And this was the genesis of Cloudant. So Cloudant was implemented using Apache CouchDB as a base, and then you can see several other open source projects were also used in order to develop this scalable, easy to use database as a service very quickly. The Cloudant interface or programming interface is via an HTTP RESTful API. And here's an example of a typical call where I can get a particular document by its ID. And we'll actually talk more about this in a few more slides. So the APIs support your normal CRUD operations like creating, retrieving, updating, and deleting documents, as well as retrieving documents via customized searches. The API, because it's HTTP based, is agnostic to programming languages, so any programming language that has the ability to make HTTP calls will be able to interface with Cloudant. It is 100% compatible with Apache CouchDB, and as I mentioned in the previous slide, it was developed on top of the CouchDB code. So let's look at some of the feature highlights of the Cloudant API. We already discussed the CRUD operations, that is create, retrieve, update, and delete. There are also primary index operations, and the primary index is available for every database out of the box. Every document has a field called _ID, which serves as its primary key or unique identifier. So you can find documents or fetch documents using this primary key or ID. It also supports secondary indexes which you provide. These are built using MapReduce, and we'll talk more about this in a few slides. But this gives you the ability to do more complex types of querying beyond retrieving documents by their ID. So for example, you can retrieve subsets of data based on the value of other fields other than the primary key or ID fields. You can do aggregation, counting, summing, and so on using the secondary indexes that you provide. And again, we'll talk more about that later. There is also Cloudant Query, a recent addition to the API that provides a mechanism for retrieving documents in a style that is conceptually similar to the SQL select statement. And we will look at an example of that later on. And finally, there's a search capability provided via the Lucene project, which allows you to do ad hoc queries by searching on documents based on their actual contents. Before we get into the nuts and bolts of the Cloudant API, there are a couple of fields that are available in every document that we need to discuss. First, there's the ID field. As I mentioned earlier, this is unique per database. Any unique string can be supplied as an ID, and if you don't provide one when you create a document, then Cloudant will generate one for you, guaranteeing uniqueness for that particular database. There's also a revision number field that's maintained by the Cloudant database, and each document has a unique value for this. It's generated using an MD5 hash of some document-specific information. And if you look at this example here, it's always prefixed by a number. And in this case, the number represents the number of times that the document has been updated. So for example, here the number is 2. So we know that this document has been updated 2 times. Whenever you're doing any kind of updates or deletes of a document, you must provide the latest rev value or the request will fail. And why this is important is this will prevent applications from updating outdated copies of documents. So if you have 2 applications using the same database, one has an older copy of a particular document and tries to update that by overriding a newer version of the same document, that update will fail. So it's very important for applications to keep track of the revision numbers, and if you do end up in the situation where your update fails because of an outdated document, you would then have to go back to the database, fetch the latest version of that document, merge your changes into that latest version, and then do the update again for it to be successful. So now let's go through the API and look at a few operations. So the first operation we'll look at is a very simple one. How do you return a single document? Well, it uses the HTTP GET verb with the name of the database and the ID of the document in the URL. And here's an example of getting a document with ID 100 from the authors database. And as you can see, it's a GET request with the appropriate URL followed by the name of the database, authors, followed by the ID of the document. Now let's look at inserting a document. There are 2 ways to do this. You can do this via a post operation or via put operation. The key difference between these 2 approaches is that when using post, you need to put the document ID in the document body, whereas with put, the document ID must be in the URL. So let's look at a post first. We would do a post including the document that we wanted to insert. And there's our ID and some other fields that we created for a document. And when we execute this, we would get an indication that everything was okay. And we also get the first revision number, the first generated revision number. And as you can see, it's prefixed by a 1 because this is the first time that this document has been written to the database. Now, if you do it via put, it's a very similar approach. The difference is that the ID goes in the URL itself. Now we have the document without the ID field, and when we execute that, we get a similar response. Now let's look at an update. It turns out that updates and creates use the same operations, put or post. So these operations are essentially overloaded. The way the semantics work is that if the ID exists for one of these operations, in other words, if that specific document is already in the database, then it's an update. If not, it's a create and a new document is added to the database. As I mentioned earlier, if you're doing an update, you do need the latest rev version or the operation will fail. And similar to a create, you can do an update via a post or via a put. If you go via post, then you need to put the ID in the document body. And as you can see here, you also need the latest revision field, or else this operation will fail. So by providing ID and revision number, I will get back a response. Once update is done successfully, you'll see that the revision number will be incremented to indicate that the document has been updated again. And like with create, you can do an update via put. Again, the key difference here is that the ID is in the URL. And as you can see here, I also have the rev field in the body of the document in order for the update to process successfully. And when I issue this command, I get back a response with an incremented revision number indicating that the document has. Now let's look at deleting a document. Delete is done using two different HTTP verbs, a delete or a put. Like with the case of an update, the latest revision number is required or the delete operation will fail. So let's first look at doing a delete via the HTTP delete operation. In this case, both the document ID and the revision number have to be in the URL because an HTTP delete does not allow any content in the body of the request. So in the case of an HTTP delete, again, I put the revision number and the document ID in the URL, and I will get back an acknowledgement saying that the delete was successful. If I do the delete via put, I need to provide the document ID in the URL. Then I have to provide a revision number in the document body of the request, along with the deleted true combination as shown in the slide in order to delete the document via put. When I execute this, I get back an acknowledgement saying that the delete was successful. Now let's look at secondary indexes. As we mentioned earlier, these allow you to do more sophisticated queries. In Cloudant, secondary indexes are developed using MapReduce, as I'd mentioned, and they allow you to return specific subsets of data that you define in the index code itself. You have to provide a map function which returns a list of key value pairs. You must have a map function for any secondary index. Optionally, you can also provide a reduce function which will reduce the list to a single value per key. The reduce function is optional. I think the distinction between the two will become clearer when we go through a specific example. Both map and reduce functions are written in JavaScript and they're stored in the database in special documents that are known as design documents. So let's look at a specific example. Hopefully this will make the map and reduce functions clearer. So we'll start with a database that's a list of cars. And here we have 5 values. Each document has an ID, it has a make, it has a model, it has a year, and it has a book value, which is the book value of that particular car. So now let's do a map function that gives me a list of all the cars' makes and their book values. And here it is. It's a JavaScript function that gets each document as a parameter, and then it has to do something. In this case, we're calling emit. And this is what the map function is actually returning. So we're returning the make and the book value. And the first thing that's returned is always the key. And everything else is considered a value. So in this case, we're creating a list of makes and book values and returning those. So we also want to aggregate the book values by make. So for each make, Audi, VW, and so on, we want aggregated book value. And we will do this via the reduce function. So in the reduce function, we simply return a sum of the values. And as I mentioned earlier, those will be aggregated by key. So for each unique make in this case, because our key is a make, we'll get an aggregated book value. So let's look at the results. So the results of the map function for each document, it will return the make as a key and the book value as a value. The reduce function, as we mentioned, will return a single value per key, and since the key from the map function is the make, for each make we'll get a single line that will add up all the book values of all the documents for that particular make. Now let's look at Cloudant Query. As we mentioned earlier, Cloudant Query is an alternative to MapReduce secondary views. There are indexes that are defined via JSON code as a list of fields to be indexed, as opposed to actual JavaScript code, which is the case in MapReduce secondary views. Here's an example of an index on the make field in our cars database. So as part of the index definition, we list the field. In this case, again, it's make. We give the index a name, which is called a make index, and we indicate which type it is. It's, in this case, is type JSON. And in the next slide, we'll talk about the different types of indexes available to support Cloudant Query. Once you do create an index, you can query it using a JSON selector that conceptually is very similar to the SQL select statements where clause. So here's an example for a selector where we want to return all the documents in our cars database where the make is VW and the model year is 2000 and later. So here you see we indicate the make as VW and the year as an expression that's greater than or equal to 2000. One thing to note here is that once you create an index, you can include additional fields in your selector when you're making the query. So here, although our index was on the make field, we could actually include the year field to narrow down our result set when we use that index. So here's some more information about Cloudant Query. There are two types of indexes. One is a JSON index, and you saw an example of one in the previous slide. These are actually translated under the covers into MapReduce secondary indexes, and generally they perform better than the other type of index, which is a text index, but they're less flexible. In particular, they have restrictions on the order in which you can sort the results and so on. Text-based indexes are based on Lucene. They're a lot more flexible. You can query the fields in any order and you can sort the results in any order. Both types of these indexes are actually stored in design documents like your MapReduce secondary index. Finally, there are two endpoints to support Cloudant Query. So after the Cloudant URL and the name of the database, there's an underscore index that is used for operations to create or delete indexes. And then there's underscore find, which is used for queries against indexes. So now let's look at Cloudant Sync. This is a built-in replication feature that allows you to have distributed copies of your data in mobile devices, remote facilities, sensors, and any internet-enabled device or server. It allows distributed or mobile apps to scale by replicating and syncing the data between multiple copies of the database. This includes databases running on iOS or Android devices, or anywhere where Cloudant or Apache CouchDB can run. For mobile development, this is particularly useful because it allows you to create a single local database for every user. And it also reduces round-trip database requests with the server, because if there's not a network connection between the local database and the remote database, the app will run using the local database. And then it will automatically sync with the remote database when the network is restored. So that's it for the Cloudant NoSQL database service. Let's turn our attention to the dashDB service. So this is a service that provides data warehousing capabilities for applications running in the cloud. So it's essentially a data warehouse in the cloud. The dashDB service in Bluemix does give you a certain free tier with up to 1 GB of stored data during the first 30 days of your Bluemix account. And then there are various other levels that allow you to extend that to meet your needs. dashDB is a relational database, and it stores relational data in a format that's optimized for doing complex queries, including data mining, predictive analytics, and geospatial analytics. Under the covers, it's powered by DB2 with Blue acceleration and some in-database analytics that were initially developed for the Netezza database appliance. It's an example of an in-memory columnar database, and it does things like compress the data to allow more of it to fit in memory, and more importantly, it's blazingly fast on very complex queries, especially those that involve a lot of aggregation. And there's also the in-database algorithms ported from Netezza that allow you to do more advanced analytics in the database itself, making it perform much better than an application could by fetching that data and doing those calculations outside the database. Finally, let's look at our time series database offering. This is particularly useful for Internet of Things devices that generate a lot of timestamp data. The time series database service does offer a certain free tier of data for the first 30 days of your Bluemix account, and then there are additional offerings based on the amount of data you need to collect from your devices. The time series database service offers very efficient storage of your time series data. So compared to other database technology, typically it can use less than a third of the space that a normal relational database would use to store timestamp data. It also offers SQL extensions that make it easier to write applications because you can do more complicated operations on time series data. It also has extended functions for handling spatial data, so you can do complex queries that involve GPS coordinates. The time series database service is powered under the covers by Informix, and for its API there's both a SQL and NoSQL JSON interface within the same database. In particular, you can use JDBC for SQL, and you can use MongoDB style queries to receive the data in JSON format. It also has the ability to move data between the two interfaces. So in summary, we looked at some of the unique features of some of the data services in IBM Bluemix. In particular, we looked at the Cloudant NoSQL database service, which is document-oriented, schema-less, and optimized for horizontal scaling. We looked at the dashDB service, which is a data warehousing service for relational data. And we also looked at the time series database service, which is a managed data store that's optimized for time-stamped Internet of Things data.